Afternoon, everyone, or good evening, or good morning, depending where you are located. And thank you very much to the IEEE Saudi Arabia section and the IEEE Power and Energy Society chapter in Saudi Arabia. And thank you all of you for being here. And the topic today is demystifying the phasor measurement unit, modeling and simulation. What we are trying to do today is explain some basic about phasor measurement units, and to clarify there are several aspects that they are not totally clear for many people. Well, before we start, as you must be aware, we are recording this session, and also the slides will be shared with all of you at the ResearchGate repository. But without further delay, let me start this presentation with a short introduction or the agenda. We will start with something very basic, a brief background about phasor measurement units, some useful acronyms. Then we will discuss about monitoring electrical infrastructure, what we call the classical one pack. That is wide area monitoring, protection, and control. Then we will talk about some of the myths, and we need to identify what is the concept of phasor measurement unit, why time synchronization is needed. Then we will discuss some standardization regarding synchron phasors to go in full details with the standard IEEE C37118. And some discussions about communications. And finally, probably the most exciting part is the use of real-time simulation for hardware in the loop and phasor measurement units, and some practical cases. The practical cases will be in real life, so I will require a bit of your patience regarding this section, okay? Well, let's start our presentation. I believe every one of you know that the electric industry has been around the world for more than 100 years. And the reality is that electrical power systems are based on AC signal, alternated currents. And these AC signals, they are produced inside the synchronous machine. The synchronous machine, the basic principle of the electromechanical device is to create, to generate, to produce AC signals, and these AC signals follow a classical sine wave. However, from the very beginning of the electricity industry, power system analysis rely on the use of these AC signals. And one of the most beautiful development of the power system studies was the concept of phasors. Charles Prometheus Steinmetz published a paper in 1893 where he presented the basic concept of phasor. And phasor, it was a very clever representation for AC quantities where the independent variable, the time, was avoided. To be honest, Charles Prometheus' statement was extremely clever, that he realized that the sine wave can be represented using complex variable. And that is the starting point of the phasor representation. The phasor representation is very simple. What we need to understand is that we have the time domain representation, and in those cases we are using the instantaneous value and we are using the sine wave. However, Charles Prometheus' statement, he said that the AC signal can be characterized by three main aspects. The first aspect is the amplitude of the signal, the second is the phase angle, and the third one that is assumed constant in the basic concept is the frequency. So what you need to understand is that the phasor is the root of all the AC circuit analysis, and as a consequence, the power system analysis. Before we move forward, it's very important that people realize that there are several useful acronyms. For instance, one of the first one that we will be using is phasor measurement unit, and the acronym is PMU. PMU is identical or is the short version of phasor measurement unit. Also, phasor data concentrator during this presentation, it will be used as PDC. Also, WAM, there is a small typo over there, supposed to be a W here. WAM is represented wide area network. WAMS is basically wide area monitoring system, and WACS is basically wide area control system, okay? Those acronyms will be very useful for you during this presentation, and let me start with the monitoring infrastructure, okay? As you must be aware, AC signals are moving inside the electrical system. But for controlling the electrical power system, we need a monitoring infrastructure. And this monitoring infrastructure has been in place for many, many years. In modern electrical power system, the monitoring and control is basically one of the most important activities of the system operator. And for many years, we rely on that monitoring and control in order to specify and to run the functionalities of the system. So that was the idea behind the network security monitoring. Network security monitoring, it is a system that is basically doing the monitoring and controlling functionalities inside the system. And one of those network security monitoring system is what we call today supervisory control and data acquisition system. What I'm talking to you is basically the SCADA. The SCADA has been used for many years as monitoring and controlling the processes, the infrastructure, and the facilities. And the SCADA basically combines software and hardware, but also communication network in order to gather and process in real data, allowing the operator to manage and to optimize the process. Here in this drawing below, you can see that the SCADA system has different elements. We have field devices that basically they are collecting signals or receiving signals. These field devices can be sensors, but also can be actuators. Then in the middle, we have the remote terminal units or the programmable logic controllers, the PLC or the RTU. And those devices are using the communication infrastructure that can be a wide area network or local area network in order to transmit signals to the SCADA master. And the SCADA master is basically where we collect, process, and visualize the data that is coming from the many devices across the field. So the SCADA has been for many years. The SCADA has several advantages like the real-time monitoring, allow the remote control, and that allow us to improve the safety, especially in hazardous environment. Also, the SCADA allow data visualization that is a very important tool when we are trying to understand very complex processes and trends in the variables. Also, one of the advantages of the SCADA is that allow the optimization of the process, alert management, data logging, and also integration with other systems. However, the SCADA has several advantages, but also there are several aspects that they are disadvantages. One of the most serious disadvantages of the SCADA is that this is a system that is interconnected with so many elements and so many communication network that there is the possibility of cyber attacks. Cyber attacks is one of the main considerations behind the disadvantages regarding the SCADA. But also there are many other elements like the complexity in designing, implementing, and maintaining the SCADA through the lifetime of the system. Compatibility issues for integrating different devices, field devices, and RTU is another of the issues. And finally, dependence of technology and regulatory compliances, they can be several disadvantages. But don't take me bad. SCADA has been in the power industry for many decades and is still in use in the electrical industry. However, the blackout of 9th of November 1962 in the United States of America create a drastic change. This blackout was one of the large blackouts in North America where more than 30 million people were affected. And the service interruption was around 13 hours. And one of the interesting things is that this very basic blackout was caused by a failure on the setting of a protection relay, and that created the event that followed the blackout. The report that was submitted to the Congress in the United States established several of the elements that caused the blackout, but also some aspects related to the possible corrections and the possible enhancement on the monitoring system in order to avoid this kind of blackouts. And to be honest, this is a very sensible document because this blackout was the origin of the wide area measurement system. That means that we are using technology in power system in order to gather real data for so many very measurement points across a very wide geographical area. With this, what I'm trying to tell you is that this blackout, the consequence of this blackout was that the electric utilities start to consider the wide area monitoring system. And together with this, in 1970s, it was the development of the symmetrical component distant relay. And the symmetrical component distant relay that was basically a device in order to calculate using symmetrical components the fault location and the fault status of a transmission line was the starting point of what we know today as a phasor measurement unit. It was the symmetrical component distant relay combined with the technology that appeared in 1980s, the global positional system. The global positional system together with the SDR, it was the point where the synchronized phasor measurement unit was introduced. And it was introduced in the mid-1980s. That means that when we are working with electrical power system, we have several dimensions in terms of time and space when we are talking about monitoring system. The SCADA that is still working in electrical power system is basically a centralized aspect of monitoring. But the time frame for that is basically minutes. Then, after the blackout of 1965, wide area monitoring, protection, and control start to be very, very useful for electrical system. Now we are talking about a time frame related on seconds, and we are talking about that is in the middle between fully centralized and localized. And here at the very bottom, we have the fastest response. In this case, we are talking about IEEE, intelligent electronic devices for protection, and that is totally local and in the sub-second region. Well, all of this is the basic introduction to talk about the wide area monitoring control based on phasor measurement units. And I will start with the first misconception. There are many people that they are totally wrong when we are talking about phasor measurement unit. And the first misconception is that people must understand that the phasor measurement unit is basically a device. What I'm talking about is that the phasor measurement unit is a device that produces synchronized phasor. Synchronized phasor is the output, is the data that is produced by the PMU. And the synchronized phasor together with frequency, a rate of change of frequency, they are data stream. What I'm talking about is that this is data that is produced in real time. And the synchronized phasor is the phasor representation with data samples using a standardized, a synchronized signal as a reference of the measurement. Here I am explaining the situation. Here you can see that we have an arbiter system. This is a 1133A, be also currents, and inside the device, the hardware is producing what we call the synchronized phasor, and that is the data that is streamed. But now let's think about what is inside the PMU. Well, when we look inside the PMU, the PMU is basically a device that initially arrives signals, analog signals, voltage for instance, and then we have the analog to digital converter. But this analog to digital converter have a very specified functionality. We are receiving a GPS signal, and this GPS signal is creating a timestamp. Together with the oscillator, this analog to digital converter is creating an stamp data that is going into the microprocessor. Inside the microprocessor, we get the basic phasor representation, and from there we are using a converter in order to show the data stream in the form of synchronized phasors. Here there are more details about the structure. Basically what we are doing is creating signal processing together with the data acquisition that is coming from the analog to digital, using the GPS receiver in order to put the timestamp, and together with the communication interface module, we are producing the synchrophasor signal, okay? Where was invented the PMU? Well, to be honest, it's very clear that the first PMU was built in Virginia Tech in the United States. And over here you can see the photo presenting the first PMU. You can see at the top the GPS receiver, then we have the PMU, the signal conditioning, and this is sending the signal, and finally we have a user interface. Well, it's clear that a phasor measurement unit is a device, a real device. And now I would like to show you, is this a PMU? And in front of you, what I am showing right now is a Simulink model. In this Simulink model, of course, we have a AC signal. Here we have a AC signal. This AC signal is going into a block, and the output of this block are the magnitude of the voltage, the angle of the voltage, and the frequency of the signal. Many people confuse this with a PMU, and that is totally wrong. It's totally wrong because first, where is the time synchronization? There is no time synchronization inside Simulink. Second, this is offline simulation, and because this is an offline simulation, we are not having any data stream. For this, I totally tell you this is wrong to calling this a PMU. In fact, MATLAB Simulink recognized that this is inspired by the standard for synchronized measurement, but this is not a PMU. In the previous slide, I showed you the PMU, and right now we can see inside the real PMU. Here I opened for you this Arbiter 1133A, and you can see this is the PMU that we will use in few minutes inside the lab. But this PMU is basically, you can see over here, digital signal processing. This is the main core of the PMU, and here we are sending the signals, the three-phase signal, ABC currents and ABC voltages. And this process, these signals, analog signals, are converted into digital, and then they are streamed using this Ethernet port over here. What I'm trying to tell you again, the phasor measurement unit is a real device. One of my old projects in 2017, we developed from scratch a phasor measurement unit. This project received the name Phasor Catcher, and Phasor Catcher is basically a low-cost PMU. And in this case, we are using 3 Arduinos low-cost single-board computers in order to create or to generate the data streaming that can be used as a phasor measurements, okay? Okay, But now, what is the second misconception? The second misconception is related with the time synchronization. And why do we need time synchronization? Well, if you remember, the PMU is based on the concept of phasors. And one of the property of the phasors is that we remove the time assuming that the phasor is rotating at constant speed. For that reason, we can say we have here the voltage 1, we can say this is the voltage 2, and this is the representation for the phasor voltage 1, and this is the representation for the voltage 2. However, in order to be synchronized, we need a reference, and that reference must be rotating at constant speed and is equal to the synchronous speed. And the only way that we can do that is synchronizing the measurements. And that is where the beauty of the phasor measurement units start to be serious. Because we are using the GPS signal, that means satellites around the world, in order to synchronize the measurement, and synchronizing the measurements allow us to put together on the same plane with the same reference all the signals. But what's happened if we don't have synchronization, or if the synchronization is affected? Well, over here you can see we have over here the phase angle between A and B. What I'm telling you is, in the previous slide I showed you V1 and V2, and here we are having the angle between 1 and 2. What is the difference if we have a synchronized measurement or if we have a second mismatch? I believe all can see over here that having a desynchronized, no synchronized signal create a different phase angle. And that phase angle is the phase angle that is defining the power flow between the 2 points. So we need to have the synchronization in order to produce the best result, or the real result for the phase angle. Now the question is, how do we have synchronization? Well, there are many ways to obtain synchronization. There are some ways that is based on pulse, radio signals, but the GPS, that is basically a network of satellites around the world, is the best way to produce a synchronized measurement. And over here you can see now the representation of the time synchronization. With the time synchronization, we have a satellite that is sending signal and receiving signals, and these signals are received by a GPS antenna. Then at the substation we have a satellite synchronized clock. That means that this clock and this clock, both of them, that they can be geographically located at different positions, 1,000 miles for instance, but the time here and the time here will be the same. So as a consequence, the phasor measurement unit will receive the time synchronized in the same reference. So when we process the voltages and we translate those analog signals into digital and we put together with the stamp, well, we create the synchronized phasor that is basically the representation of these AC quantities in a synchronized framework using satellite signals in order to keep synchronized the measurement. And that is the synchronized phasor. Okay? Perfect. Now let me move forward, and what I will do is I will discuss some typical synchrophasor measurement systems, okay? Well, you need to understand that the weight area monitoring system started in 1960s or 1970s, and the first application was monitoring. At the very beginning, we started with the wide area monitoring system. That's basically is recovering signals, measurement signals coming from the field from different geographical locations. And then they are received and they are processed. And the typical wide area monitoring system have essentially two basic components. the data acquisition, that is basically the PMU, but then we have the data delivery and the data processing. In the next slide, I can show you what is the typical infrastructure. Over here, you can see a block diagram that we have so many PMU across the different places, geographical places. It can be all the PMU installed in one country, and then they go to a very important aspect, and that is the Phasor data concentrator. The Phasor data concentrator is a very specific use computer that they receive the data stream coming from the PMU, and then they produce real-time and time-aligned output. What I'm trying to tell you is that the data concentrator receives the data stream of many PMU, and then they produce a data that is also time-stamped and synchronized that they can be sent to the super data concentrator. The super data concentrator, they are basically a centralized concentrator, a very specific computer that we can use, for instance, for processing all those data streams, but also for storage or to run applications. For instance, if those PMU are receiving signal for frequency in different locations, and then we can send a vector of those frequencies to this data concentrator, we can run here a wide area under frequency load shedding, because here we can concentrate all those signals, and then if an event happens, we can send trip signals to the devices. What I'm telling you is that the super data concentrator is more than a computer, and inside that computer we can run some applications using the data stream coming from the Phasor measurement units. But now, what is the standard that we use to characterize the Phasor measurement unit? To be honest, the history about the standardization of the synchro phasor for power system started in 1990s. In 1995, the first standard was the IEEE 1344, and it was basic a standard to define time synchronization, data sampling requirements, but basically we follow a format similar to the ComTrade. You must remember that the ComTrade is a format that is used for dynamic measurements, especially for interchanging data. However, the 1344 standard was succeeded by what we know together today as ANSI C37118. The ANSI C37118 is the IEEE standard for synchro phasors in power system. And this standard is divided into basic standards. The C37118-1, that is basically for measurements, rock-off, and dynamic operation, and the C37118.2, that is basically for preserve the data change, but also there are some improvement regarding flag and configuration. So we have the two standards, and what we need to understand is that both of them cover what we know today as synchronized phasor units. Okay, but now, what is the definition of synchro phasors based on the standard? Well, it's not different to the definition that, Charles Prometeo statement created in that paper of 1893. It's basically a magnitude and a phase angle. However, the way that the phasor is created require that this number is stamped with time. And this is another of the numerical results coming from offline simulations. For instance, many people run simulations using the Xylem Power Factory, and then they export the results using a time series. In a time series, we have a a column that is dedicated for the time, and the other column that is basically, for instance, defining the angle. As you can see over here, that is the structure of this file. We have time here, and we have one variable, in this case, phase angle. However, that is what I call fake PMU data, because there is no synchronization over here. There is no one very important property of the PMU data, and that is the grab angle. In a minute, I will explain what is the grab angle, but here you are getting is a process angle coming from a offline simulation. That is never will be identical to a data stream coming from a phasor measurement unit. Okay? I was talking to you and telling that with PMU data, the data streams, they follow what we call here the grab angle. What does mean the grab angle? The grab angle means that when we are measuring the phasors, they are restricted in an angle that is from pi to minus pi, or if you prefer, is restricted to 180 degrees minus 180 degrees. However, if you are using offline simulation, typically the angle is growing or decreasing and never stop that pattern. So again, what I'm telling you is that the PMU data is very, very different to the data that is obtained for an offline simulation. And more than that is because the real PMU data is coming in a data stream. That means that is produced in real time and is sent into the network, local area network, in real time. And they follow the format that is basically following the standard IEEE C37118. Here, for instance, I can show you that we are using a very specialized software, and this software is capturing the data. One of the software that we can use is the PMU connection tester. We will do this in a minute in the lab, but basically this software is looking into the local area network and capturing the data coming inside the digital network, the local area network, following the standard C37118. Another software that can be used in order to analyze the packet coming from the local area network is Wireshark. Wireshark is another software. They allow you to analyze each one of the packet, and inside the packet you will see how the data is structured and how the data is moving inside the network. Okay? Well, but why we need in communications with phasor measurement units? Well, this is another of the misunderstanding. Many people believe that the phasor measurement units are similar to an offline simulation. And the reality is that the data coming from a PMU or phasor measurement unit is communicated using digital network communication. In that digital network communication, we have a very small unit of data that is called the packet. And the packet is basically transmitting the information inside the local area network, and this can be using, for instance, TCP protocol or UDP transport protocol. And each one of the packets have a very specific structure. And over here, for instance, I am telling you one of the sections related of this packet. And in this case, we are talking about the data frame organization. And as you can see over there in the table, you can see that there are some size for bytes, the field name, and some comments. For instance, if we are analyzing data coming from a phasor measurement unit, the first field that you will realize is the synchronization. And in this case, this field will give you the synchronized byte followed by the type and version of the synchronization. So this data must be analyzed and is not possible to be obtained when you are using classical offline simulation. The only way to get that information is using a software like White Shark that allows you to get that data in real life, okay? Well, now what I will tell you before we go for the real demonstration, what I want to show you is some real uses of phasor measurement units. What I want to show you, for instance, is this first paper. This paper was published this year in the IEEE Power Energy Society General Meeting in Orlando. And this is a cyber-physical framework for system frequency response using real-time simulation and phasor measurement unit based on C37118. And this is a cyber-physical system. In this cyber-physical system, we have a real PMU here that was connected to the GB system. That means that this PMU, that is the arbiter 118, is receiving the three-phase signals, and those three-phase signals are transformed into data that is streamed using the C37111 protocol. And here we have a real-time simulator, and this is my beautiful OPAL-RT 4512, that is basically the real-time simulator where we are testing our frequency controllers. And finally, we are publishing that data, or that data can be stored using a basic network capture, okay? And here is the other part of the system. Inside the real-time simulator, we are receiving the signal, and we have an enhanced frequency controller, and we have the model of one battery. So the signal coming from the GB system is processed in the PMU and then sent into the real-time simulator. And inside the real-time simulator, we have a controller, frequency controller, and we have the battery. And the product of that is that we can assess the power produced by the battery, the state of charge, and signals like the voltage and current. And here in this paper, you can read more details on the paper, but here you can see the electrical signals coming from the real-time simulator and coming from the PMU in order to see the real performance of the system. Another application is the cyber-physical testbed for co-simulation, but in this case, this was created with José Miguel Riquelme from the Universidad Politécnica de Madrid. And basically, what we are doing here is a co-simulation in real time. We have a real-time simulator coming from Typhoon Hill. We have a real-time simulator coming from OPAL-RT. We are communicating them using digital local area network, using classical Ethernet, but the communication is performed using synchronized phasor C37118. In other words, what we are doing is very simple. Inside OPAL-RT, we have a power system, and in this case, the power system is the classical PM Anderson 9-volt system. And in this system, we have some measurements coming from what we call phasor measurement unit from Simulink, but this data is streamed and synchronized using the real-time simulator. And in this case, we are using the signal to transfer the data between the OPAL-RT, sending the signal to the Typhoon Hill. And inside the Typhoon Hill, we have the full model of one under-frequency load-shedding scheme. In other words, what we are doing is interconnecting the real-time simulators using the C37118 protocol in order to show you the use of this test bed. Here you can see the physical real configuration. You can see the location of the OPAL-RT. You can see the configuration with the Typhoon Hill and then some results, okay? Now probably is the most exciting part because I will start the practical demonstration. We have 20 more minutes before we finish, and I will start the practical demonstration. The first demonstration is extremely simple. The first demonstration was created by my PhD student, Linan Hai, and he is a PhD student at the University of Southeastern Norway. And what we are planning to do is something very simple. The idea is that we will inject AC analog signals to one very famous ID. In this case, this is one of my lovely relays that they are located in Norway. This is the SEL411L. This is a differential line protection, but this device can be enabled in order to create PMU data using the standard C37118. And the configuration is like this. If you look over here, in a minute, I will tell you that we are using the Hill 604. We have a test model, and we are using this real-time simulator to create low power signals that they are going to the Typhoon Hill Universal Connect. Here we are amplifying voltage and currents that they are suitable, that they are ready to be applied to the real relay. And in this case, the SEL411, it will create data streaming using synchronized phasor, and that data will be streamed inside the local area network in the lab. And that data streaming can be processed in another real-time simulator. However, we are not doing this today because I will not demonstrate one algorithm that we are developing, okay? Now what I will do is, let me stop this presentation, okay? Let me stop the presentation, and right now what I will do is I will connect to the lab in Norway, okay? Right now we are connected remotely to the lab, the DHenSys lab in Norway. And over here you can see the Typhoon Hill Control Center. And right now we are connected to the real hardware in Norway, the real-time simulator, the Hill 604. Now what I will show you is the network model that we are talking about. Here, what you can see over here, let me zoom out a bit. Here we have a small network. As you can see, there is external grid. There is a bus bar, a step-down transformer, another bus bar, some loads, commercial and residential. Then we have here the SEL411 communication, then a transmission line, and then finally 2 loads. What I'm telling you is that this is the network that we are planning to simulate today. And here, as you can see, let me show you. What we are doing is collecting the voltage and currents coming from the network. And with that, we are transmitting those signals to the beautiful Hill Connect. And with the Hill Connect, what we want to do is send the signal to the real relay. Okay, let me do this. We will compile this model, and when we compile this model, we are using the Hill SCADA, okay? Right now you can see over here, this is the Hill SCADA. This is basically the transformer, and here in real signals. What I will do is something very simple. All of you must be aware that we can access the relay using the web-based interface. In this case, I can put here the password, and you can see over here, I am logging into the relay. And let me go here to the synchrophasor signals. As you can see over here, the voltages are 0, And as you can see over here, the currents are 0. What I'm trying to tell you is at this moment there are not currents or voltages going into the relay. But what I will do right now is I will start the real-time simulation. When I start the real-time simulation, I believe all people can see that the breaker right now is green because the breaker is sending an open signal to the circuit breaker. But at this moment, we are applying voltage to the high voltage side of the relay. And what I will do now is I will reset the relay, sending a signal to the relay. And right now you can see that this is in red color. Red color means that right now the circuit breaker is closed. And let's see here what is, let me see. No, sorry, I made the mistake here. Let me reset the relay and send the signals. Let me restart the simulation. I restart the simulation. Right now, let me send the signals to the relay. And over here, you can see, voila, we have 230 kV, 230 kV voltage going into the terminals of this relay. Because in this case, the circuit breaker is open and we are receiving voltages from the voltage transformer. However, to close the relay, I am closing the relay. Right now, you can see here in red color, that the circuit breaker is closed. And if we go to the web interface, you can see over here, there are 6 amp on the phase A, B, and C. But what is really interesting is that right now, for instance, I can simulate a fault in this system. And right now I send a fault to the relay. And right now the relay is open and we can see back that the voltage is still 230, but there is no current at the relay, okay? You can see over here that the circuit breaker status change from closed to open. And you can see over here the currents that they are going into the relay. Let me reset let me remove the fault. Let me reset the relay, okay? Probably some people, they don't trust me or they don't believe that the relay is receiving these voltages and current. And the other way that I can show you, that the relay is receiving signals is basically going to the accelerator. The accelerator is the software coming from SEL, from Schweitzer Engineering Laboratories. And over here, we can access remotely the relay. In particular, what I want to see is the human-machine interface. And in this case, what I will do is basically disconnect the relay from here. And now what I will do is connect to the relay. And right now we are connecting to the IP address 192.168.117. And right now I will go to the human-machine interface. Tools, human-machine, yes. Why is not opening? Okay, let me see if the connection is working. Connection is working, perfect. And the relay is connected. And let me see what is happening here. Let me restart again the accelerator. And let me connect to the relay. And from there, I will show you the phasors in the human-machine interface of this 411L relay, okay? What I will do is I will connect to the relay. Right now, we are connected to the relay. Now, what I will do is basically go to the human, come on, human machine interface. Yes, right now it's opening. And in front of you, you will see the equivalent to the real relay. In this case, we are establishing the connection. And what I want to show to my people here in the audience is the phase components. But let me go to the real-time simulation. Yes, the real-time simulation is running. You can see here at the bottom that the real-time simulation is running. You can see that the circuit breaker is closed. And over here, you can see the currents and the voltages, okay? You must remember that we are applying 230 kV. You can see the phasor diagram, and you can see over here the current 6.6 amps, okay? Well, this is a very basic demonstration, and the idea behind this demonstration was to show you that we can use the real-time simulation in order to send signals, analog signals to the PMU, and then we can collect that data using the data stream, using the proprietary software, okay? But now let me go to the second demonstration. The second demonstration is probably the one that I love to show to everyone, because the second demonstration is using the phasor measurement unit from Arbiter system, in this case the 1133A. But in this case, I will show you another of the myths that people don't understand about phasor measurement unit. The idea here is that we are using this 1133 Power Sentinel, the Arbiter device. It's probably the oldest device that I have in the lab, but this device has been with me and working properly. What we are doing is basically connecting or wiring this Arbiter to the real-time simulator using the power amplifier. In this case, we are using the Typhoon Hill again. We are using the Hill 604 that you can see with the number 1 here at the top. Then the power amplifier, we are using the wiring. You can see over here the voltage and currents wires that they are connected on the rear of the phasor measurement unit. And at the end, the test, what we are planning to do with the test is we are using a test model. The test model is sending the signal to the Typhoon Hill Universal Connect, and from there we are generating high-powered analog signals, voltages and current, three-phase voltages and currents, going to the PMU. And from there, we are streaming synchronized phasors that they are going to the local area network. And I have one computer that will be connected to the local area network, and I will use the software of the Sentinel or the Arbiter system PMU in order to show you. Now let me do that. Let me connect to the lab in the UK. Right now, let me connect again here. Yes, reconnecting. I am connecting to the lab that is located here in the UK. Let me show you what we have here. We have a test system that was created using a very simple system, and the system is able to control voltages and currents, and those voltages and currents, they are going to the Hill Connect interface. Then we can use this interface, this SCADA system, in order to show you the data that can be controlled, voltage, frequency, angle, or currents can be controlled using the real-time simulation. But before running the real-time simulation, I would like to show you this proprietary software coming from Arbiter system. Arbiter system have this beautiful software that is called the PSCSB. And with this software, what I can do is connect to the real PMU device that is inside the lab. And right now I am connected to the PMU. I would like to show you some phasor measurement unit data. And what I will do is I will record and I will measure this data. Right now you can see over there, this data is crazy because at the moment there is no voltage applied or currents applied to the phasor measurement unit. And you can see over here that again, the frequency data is crazy because there is no voltage applied to the phasor measurement unit. However, what I want to do is right now, I want to run my real-time simulation. And right now, let's say that I want to apply, let's say I want to apply 24 volts to the phasor measurement unit and a current of 0.2 amps, okay? Let's say 0.2 amps. You can see that inside the real-time simulator, I am sending 50 hertz, 25 volts, and 0.2 amps. But let's see if that is what is happening with the real-time simulator. Oh my goodness! Look over here. This is amazing. This is amazing. You can see over here, let me do the following. You can see over here the magnitude 25, almost 25. You can see over here the voltage B and the voltage C. Let me show you only the voltages, okay? You can see over here a beautiful three-phase system. You can see phase A in light blue, then you have phase B in black, and then you have phase Z in yellow. What is interesting is that you can see that the phasor diagram is static, is located in a fixed position in this place. And that is because basically you can see that the frequency is almost constant to 50 hertz. And if we want to see the currents, now let me go back here to the phasor diagram and let me show you only the currents. Now we have currents. You can see 0.2, almost 0.2 amps on A in blue color, green color 0.2, and pink color 0.2. And the frequency is still almost 50 hertz. But now what I want to show you, let me go back here and let me do something that is very critical to understand. What's happened if the frequency is different to the rate frequency? What's happened, for instance, if now the frequency is below 250? And what I will do here is I will set up the frequency to 49.9. Let me use here 49.9. And let me see what is happening with the phasors. Wow, this is beautiful. Because the frequency is below the rate frequency, the angle in the phasors are lagging the reference. And you can see now how the phasors are rotating in the clockwise direction. And this is beautiful because right now in a classical offline simulation, the phasors are referred to the local reference. So here now let me do the following, and we are almost closing this demonstration. Now let me go back here and I would like to increase the frequency 50.1, and now the phasors will be rotating on the other direction. As you can see over here, right now the phasors are rotating anti-clockwise. And the reason that the phasors are rotating anti-clockwise is because now the voltage A, B, C, the frequency is larger than the reference 50, so the phasors are leading the reference and they are departing because they are rotating faster than the reference. And this is beautiful. Again, this is something that you only can see in this kind of real-time simulations and using real hardware, like in this case we are using the Arbiter 1133A, and you can see over here the data, okay? Finally, I would like to do something. Let me show you something. I will put here back the frequency of 50. It's no a problem. And now what I want to do is open this beautiful software. I'm not sure if you are aware, but this software, the Wireshark, is probably the best known software for network analyzer. I mean, if you have a digital network, a local area network, you can see how the information is moving inside the network and what kind of data are moving inside the network, and using this software, okay? What I will do is I will sniff, I will try to see the packets inside the DHensys lab network in the GB system. And right now, what you can see over here, is there is TCP, TCP, classical TCP communication, okay? What I will do is I will use a very famous software also that is called the PMU connection tester. And the PMU connection tester is basically a software that I can use to connect to the PMU. This is another software. This is an open access software. And you can see here the frequency is 50, okay? Let me do a trick over here to show you. Let me put the frequency 53 Hertz, because probably the people will not believe me. Let me put here 53 Hertz, and let's see the frequency here in the PMU connection tester. Right now you can see here that the frequency in the PMU connection tester is 53. But what is relevant is right now I would like to see the packets inside the local area network. And let me stop here the capture, and I would like to show you some packets coming from synchrophasors. Because inside the digital local area network, the data that is produced by the real phasor measurement unit is moving. And in this case, you can see over here that we have the packet, and inside the packet you can see the information that I was talking during my presentation. We have the synchronization word, we have the frame size, and also we have the PMU data inside this packet, okay? Well, I can spend here probably a week talking about this software and how we understand the PMU data, the real data stream, but I believe we are running out of time at this moment, and what I will do is basically stop this real-time simulation, and I will come back to my presentation. Well, this is the very end of my presentation, and the closure is basically some conclusions and some key ways that I want that you take. The first thing is the PMU is a real device. And this real device is creating real-time data. And this real-time data is a data stream that is moving inside a digital communication network. And this digital communication network is following a very specific protocol that is the IEEE C37118. It's not fair, it's not right to use data coming from offline simulation and say that that is a PMU data. It's not. The first reason is that data is not time stamped. Second, that is not real-time data. It's not a data stream data. So please stop using offline data and say that that is data coming from PMU. Well, this is the very end of my presentation, and I believe we have some time for questions and answers. Thank you very much for your attention. Let's start with questions and answers.